Okay, so we're going to go on to the next section of Unit 2 notes here, and that is about the cousins to potential and potential energy, or excuse me, the cousins to field and force for electricity, and that is potential and potential energy. Okay, so let's get started here. Okay, so when last we met, we had been talking about the Coulomb's law of force with the electric field, and then we talked about the electric force, and we saw how those two things were related. Well, it turns out that there's two other properties that are also related. These are scalar properties, though. So these are properties that you have to incorporate the sign of the charge as you solve the problem in order to get the right answer. So until now, we've only used the sign of the charge to figure out which way to draw our vectors in our pictures. Now we don't have any pictures. Now we just have straightforward scalar calculations. So some people find this a little bit easier, although initially it can be a little bit confusing. So when we talked about the Coulomb's law of force, we said that there was a force on this test charge in an electric field. And if you remember from Physics 1, there was this thing called the work energy theorem. And the work energy theorem said that if work was done on an object, that means its energy changed somehow. It was either increased or decreased depending upon whether the work was done, positive work was done or negative work was done, or if work was done on the object or it was done by the object. So we had all of that in Physics 1. Well, we've got work being done here, and just because it's done by electric fields and electric forces doesn't mean it's any different than any other type of work that we can consider. So the force does that work, and what that does is it'll make a deposit or a withdrawal in what I like to call the energy bank. Okay, so if positive work is done, it has the effect of increasing the energy bank, making it more energy in the bank, and if negative work is done, then it decreases it. So we just have to figure out what type of work is done. Now, unfortunately, it's a little bit easier to figure that out when we talk about the work done with other types of charges, or excuse me, with masses rather than charges, because with masses, there's only one thing we have to figure out: which way is the mass moving? With charges, it's not just which way it's moving, but is it a positive or negative charge? Because remember, we talked about with electric field, it would go with the field or against the field naturally, depending on its sign. So we have to be careful when we talk about the direction it's moving in the charge. As you can see in this picture here, we've got a negative charge and a positive charge. Naturally, they want to be closer to each other. So just like the ball would naturally fall to the ground, if I want to move that positive charge away from that negative charge, I have to do positive work on it. In other words, I increase its potential energy, just like if I were lifting a book up. Now, the only thing I don't like about this picture is it doesn't show you a negative charge next to a negative charge. In that case, I have to force that negative charge to stay there. I'm moving it toward the other negative charge. So I have to apply my force in a different direction. So when I move a charge around in an electric field, I either remove energy from the charge or I add energy to it. So it just depends upon what I've got going on with my electric field. Now, when I talk about this, I have to keep both of these things in mind. So when you're working your problems, you do keep the sign of the charge as you are working the problem. You need to keep that as part of your calculation, because that's going to make a difference when you get your final answer. Now, but once we get that number, it's just a plain old energy that we can use just like we used in conservation of energy in Physics 1. It's not any different. It's measured in joules. It's not any different than what we already talked about. Okay, so an example of this would be like a ball rolling down a hill. It's going from a region of higher potential energy to lower potential energy. So by losing potential energy, it's gaining kinetic energy. In the case of this picture, the top part of this picture, you've got a positive charge being held close to a positive plate where it does not naturally want to be, but then there's a negative plate, so when you let it go, it's going to rush toward the negative plate, decreasing its electric potential energy. But as I trade that potential energy, I'm increasing kinetic energy. So it's the same idea. So in this case, it's a positive charge. It's going with those blue field lines, and it's going in a direction of decreasing potential energy, okay? Now, if we calculate the work done by a test charge, we're going to start out with the simplest case of the work done by a constant electric field. And that's, remember, why we like those parallel plates, because the electric field in between those is a positive number, or excuse me, is a constant. So I don't have to worry about changing electric field as I move through space. So work done is going to be done by a constant field, which means the force is constant. And if you remember from Physics 1, it's really easy to calculate the work done by a constant force. It's just the force times the displacement times the cosine of the angle between them. Because remember, you had to worry about the cosine because you wanted to make sure that you got only the component of the force that was acting in the direction of the displacement. That was the only part that did work, or parallel to the displacement, I should say. So the simplified version of this is when we let something go in an electric field, what happens is the work done is done by a force that is going to be in the same direction as the displacement. Okay, so if I know the force is caused by the electric field, then I can take the formula that I got in the last set of notes for a constant electric field, and that is just, remember, the test charge times the constant electric field. Then my displacement would be in there. Now, what I can do, though, is I can go back and remember what the electric field of a point charge looks like, and I can put that in for E in this equation. And if I do that, I get a formula that looks like this. So remember, the work is the negative of the change of the potential energy. So by finding the work, I can find the potential energy. So notice here, this looks a whole lot like the Coulomb's law force, except there's no magnitude signs and there's no r squared, because the displacement that was in the work equation canceled out one of the distances in the denominator. So I'm left with just r instead of r squared. I don't have the magnitude signs here because I need the signs of the charges now to get the right amount of potential energy. So if I have a negative charge, I need to include that in my calculation. I need to include that negative sign in my calculation. But this is just a regular old potential energy measured in joules, just like any other potential energy would be measured for you. So it's not any different once you get through this calculation here. Now, if I've got lots of charges, you might remember from the previous set of notes, I had to go through a big problem of solving vector equations and doing the component method of vector addition and all that good stuff. I don't have to do that here. All I have to do here is add up numbers, because since the potential energy is a scalar, all you do is you find that term that I just showed you, U is equal to K Q1 Q2 over R. I just solve that for every single unique pair. So if I've got all these different charges, I just sum up the pairs, because the energy between 1 and 2 is the same as between 2 and 1. So I don't need to add a second term for that. Okay, so what I do then is I total up all those terms. Some of them will be positive, some of them will be negative, no big deal. And then that gives me my total energy. So very straightforward, much easier than doing force where I had to do vector components. Once I know that, I can find the work done. Remember, the work is the negative change of the potential energy, like I learned in Physics 1. So nothing new or surprising, hopefully, there. And once I know what that is, I can find the change in kinetic energy if I want to. I can take that to find the change in kinetic energy. Now, what we do is sometimes we don't care about, just like in physics 1 when we talked about this, sometimes we don't care about the actual individual values of the potential energy. We just care about the change between point A and point B. Okay, so sometimes I don't care if I've got change of potential energy, the total value of it, because the change is all that matters. The individual values don't matter, but the change is what matters, because that's what's going to determine things like the potential difference, or what we're eventually going to call the voltage. Okay, the other thing that we can do here is, just like with gravity, since the electric Coulomb's law force is a conservative force, in other words, it doesn't rob energy from the system, it only depends on where I start and where I end, not where I go in between. If you remember in physics 1, gravity was like that, the spring force was like that, but something like friction wasn't. It was a non-conservative force, and it stole energy out of our system. If you remember, sometimes we had to worry about the loss of energy due to friction in a system because it took energy out of the system by converting it into heat. Now, when we talk about the work done, we need a reference point. Okay, we need a reference point. Teddy, shush. Teddy, no. We need a reference point. And so in physics 1, we usually use the lowest point, the ground or something like that. We use that as our reference point for potential energy. Here, what we're going to do is basically use infinity, or sometimes they'll say very far away in the problem, and that's going to give us our reference point. So that's where we're going to start with a charge at infinity and assume that it has a certain amount of energy, and we're going to move it in to the other point we're interested in and calculate the energy there. If it's very far away, that R term is going to be so big that it's going to make the potential energy out there basically zero, just like it was sitting on the ground in physics 1. Okay, so what we're doing is we're going to break this up and look at the work done by the field on a test charge. Okay, so if the field does positive work, then we have a positive change in potential energy. If it does negative work, we have a negative change in potential energy. So fairly straightforward to figure out. And we're going to have to identify the 2 points. So remember, we don't care about where it goes in between, just where did it start and where did it end. And again, just as a reminder, you have to keep track of the sign of the charge. Now, just like we had a force that had a thing that caused it, which was the electric field, the potential energy has a similar quantity called the potential. Now, these are terrible names for it because people get those two mixed up. But field and force have those cousins. So force and potential energy are related. And so field and potential are related. You have to have an electric potential to have electric potential energy. So just like to have gravitational potential energy, you have to be above a certain reference point or below it, okay? You have to have a gravitational potential. So here we have an electric potential. We don't call it gravitational potential in physics 1, and maybe we should. We just usually call it the gravitational field. So things with gravity have a gravitational potential energy because of their location relative to that reference, that zero reference point, or what we would call their height. And remember, we have positive height or negative height. So things have electric potential energy based on their location in this electric field. So leave the cat alone. Sorry about the dog barking in the background, y'all. Now, electric potential is like the energy per test charge, just like electric field was the force per test charge. Okay, so that's how they're related. Now, we have to keep track of the sign again. We have to keep track of the sign of the charge because a positive charge is going to have a positive electrical potential and a negative charge is going to have a negative electric potential, just like when we talk about the polarity, say, of a battery. We have a positive and a negative terminal. And so this is where that stems from. Okay, so another way we can write it is the potential energy per test charge, just like if we solved for E from the previous sets of notes, it would be force divided by the test charge. Okay. Excuse me. I'm going to take care of this real quick. Sorry, one of my dogs likes to play with cats and they get a little loud sometimes. So when we talk about this electric potential, what we do is we look at the units, and it's joules per coulomb, but then it's something we call a volt. So this is where we're going to get voltage from. It's from electric potential at one point. Except when we talk about voltage, again, we're not interested in individual values. We're interested in the difference between the two poles. So when you have a battery and it's a 12-volt battery, I don't know what those individual values are, but I do know that the difference between the two poles is 12 volts. So that's why it matters whether it's a 12-volt battery or whatever. It doesn't matter what the individual numbers are. We just need that difference, because that difference is going to be what does the work that we'll need that battery to do. Okay, so what we'll do is we'll do a little demonstration here to look at the work, the idea of work moving across a potential difference. Okay, so let me stop my sharing. Okay, so this is a little silly cartoon, but it shows you what's going on inside a battery. Right now, the potential at both ends of this battery are the same, because if I counted all of these blue dots, they would have the same number, and these blue dots represent my electrons. Remember, we're talking about the free electron model where the electrons are the charge carriers. So these are my free electrons. Now, if I want to create a potential across this battery, or a potential difference, I need more electrons on one end than the other, because if you think about a battery terminal, it has a negative and a positive end. Okay, so let's say I want a voltage like this, so I'm going to increase the voltage. Okay, so now what I'm doing is I'm changing the potential by moving electrons from one end to the other. Okay, and that creates a potential difference across the two ends of the battery. All right, or if I want them to go the other way, I move them to the other end. Okay, now, so what that means is the individual values really don't matter. I don't really care how many electrons I have at either end, as long as the difference between the two ends is what I need for my battery voltage. Okay. All right, so that's just a little silly cartoon to kind of show you how that sets up. So let's go back to our PowerPoint here. All right, so when we talk about this, we're usually more interested in the potential, what we call the potential difference. Now, notice that, remember that the work is negative the change in the potential energy. And we always did the potential energy is B minus A. So if I pull that negative sign in, that's why it's A minus B in this formula, because I've pulled that minus sign into the formula and flipped those. So it's just the difference in the potentials between the two places. Now, sometimes you'll know those individual values. Sometimes you can calculate those individual values, like with the formula that we saw in the previous slide that was for a point charge. Sometimes you won't know that. Sometimes you'll just simply know the potential difference between the 2 points. So it depends on the problem, what you know. Kind of like sometimes we calculated the electric field for point charges, and sometimes we calculated it for like a sheet of charge or whatever. Okay, so this potential difference is kind of like the difference between altitude levels, say on a topographic map or a contour map. So if you were to change your altitude, you would know that work would have to be done either against gravity or with the force of gravity, depending on which way you were moving. So sometimes it's just as simple as knowing the two values of potential and subtracting them. Sometimes you have to use the equation for the potential energy of a point charge and then subtract them. And sometimes you're just told this is the potential difference between these 2 points. So it just depends on the application of the problem, but it's very much like moving between 2 different altitudes on a topographic map. But sometimes we might know the electric field. And if we know the electric field, there is a way for a constant electric field that we can find the potential. And it goes back to that concept of the capacitor and the sheet of charge or the plate of charge. And remember, I said it was going to be useful and it's going to show up several times. Well, here it comes again. Okay, so if we know that the field is constant, you can find the potential by knowing how far you move through the field. So if you know the field is constant and you know the distance you've traveled or the displacement you've traveled through the field, I should say displacement, it's not the distance, then you simply just multiply those two together and that gives you the potential difference between the 2 points that you're interested in. It won't tell you the individual values, but it will tell you the change. Now, again, we're going to talk about parallel plates here, and we're going to see capacitors again in a unit or in a section all to themselves, but that's what they are. They're large sheets or plates of charge, and they have a constant electric field between the plates, and they're usually separated by a distance d. Now, we can see here that if I make the plates separated by a larger distance, then the potential difference between them is larger. So the voltage then we would say would increase across the capacitor. Now, another phenomenon that we deal with when we talk about potential is what's called an equipotential surface. An equipotential surface is the reason Mr. Squirrel can run down the electric lines and not get fried. Okay, but if he accidentally has one foot on the electric line and reaches for another one, then he's in trouble. Okay, equipotential surfaces are just like staying at the same altitude on a contour map. No work is done. If you stay at the same altitude on a topographic map, then you are not having to do any work against gravity because you are not changing your altitude. So an equipotential surface is a line or a surface where instead of the gravitational potential energy being constant, the electrical potential energy is constant because the potential, the V, is constant. Okay, so the reason this matters is if you stay on an equipotential surface, no work is done on you by the electric field or by the Coulomb's law force. And that also will eventually mean that no current will flow because there's no, what we have to have a current flow is a potential difference or a change in V. We don't have that, there's no current flow. So that's why Mr. Squirrel can go down the electric line. Okay, so if a charge moves along the surface, such a surface, there's no electrical work done because we're not changing basically our electrical height. Now, the equipotential surfaces are always perpendicular to the electric field at a given location. So if you go back and think about our point charge, which had the electric fields pointing radially outward like sunburst rays or radially inward, depending on if it was positive or negative. What that means is the equipotential surfaces there are spheres. They're nested spheres around that charge. So as long as you stay on that surface, no work is done. Okay, so how charges move in a potential then has to do with whether they're positive or negative. So if you let a charge go, it is always going to move toward a region of lower energy. Just like a ball will always roll downhill. It won't ever on its own roll uphill. So if you let a charge go, it's going to move toward decreasing energy, but that may not mean decreasing potential. Okay, because if you think about the way they would naturally move, positive charges go with the field lines, so they're moving down the electric hill, they're moving away from the source of potential. So they're moving toward a region of lower electric potential and lower energy. But a negative charge is going to do the opposite in terms of the potential. Its lower energy position is actually where the potential is higher because it would want to move toward that source of potential. It wants to move up the field, opposite the field lines. So it's moving, its lower energy state is to move toward a region of higher potential. So that's why it matters whether it's a positive or a negative charge. Now, one little sort of side note that we'll talk about simply because it's frequently seen in medical applications, particularly nuclear med or radiation therapy applications, is a unit called the electron volt. The electron volt is a unit of energy, and it's defined as the amount of kinetic energy that is given to an electron, so one electron, as it moves through a potential difference of 1 volt. So you can imagine that's not very much energy. So if I take the kinetic energy, or if I find the energy, it's Q times V, the charge of the electron times the potential energy. The electron volt is a tiny little value of energy. It's 1.6 times 10 to the minus 19 joules, because really I've multiplied 1 electron, or 1 charge of an electron times 1 volt, okay? So an electron volt is a tiny little unit of energy, but a lot of times in different medical applications, you will see kilo electron volts or mega electron volts, which are called MEVs, and so on. You'll see those show up, particularly when you're doing X-ray stuff or radiation therapy or nuclear medicine procedures. You may see the electron volt show up as a unit because those procedures have tiny little amounts of energy, but instead of writing these tiny little numbers, they'll convert to electron volts. But if you have a problem where you are given a number in electron volts, that is not an MKS base unit. You have to convert to joules before you do the problem. So we remember MKS is meters, kilograms, seconds. That's our base units. So we have to convert to joules before we do any problems if we're given electron volts. Okay, and then this is just a little cartoon like we saw before. A lot of times this is how they'll create electron beams for electron beam therapy. Okay, so if you work in radiation therapy, you may see an electron beam machine, and this is what they do. They use a capacitor, positive and negative plates, to accelerate electrons to give that beam enough energy so that it can destroy the tumor or whatever. Another application of moving things to a potential difference is using a capacitor situation to accelerate electrons to create X-rays. Okay, so you accelerate these electrons in a machine of some kind, and they hit a target, and that when they smack that target, they release X-rays. So if you're going to be an X-ray technician or work in X-ray imaging therapies or imaging positions at a hospital, you're going to use electron volts, or you're going to use potential energy and potential. And then this is just some different things that they use E-beam for. I thought it was kind of interesting. Okay, so that is the end of this set of notes. So I'm going to stop the recording. And if you've got any questions, don't forget we have our problem sessions each week, and you can come by and get some help with your problems.